Okay, I'll try to make this quick. This is a rough sketch of the motor, of a sort of motor that was used back in the mid-1920s, and variations of this all the way up into the 50s. I've for a speaker, a loudspeaker. I've seen variations of many different variations. I've got a small, transistor radio, made, late 50s, the early 60s, that uses a scheme similar to this, a bit more simplified, but works similarly. It's where what we're looking at here is just a rough sketch. It's not to scale. Just hope it gets the point of how these things operate. They're a little bit differently than what we're used to, speakers-wise, loudspeakers, where you had a voice coil, shown in red here, and surrounded by a magnet. And the voice coil itself moves, which is attached, of course, to the cone. These don't work like that. The coil is stationary. The magnets don't move. It has a independent armature. It's not a magnet until you put current through this coil. Again, the coil is stationary. It's mounted to the frame. Same with the magnets. This here is the speaker cone. I'll get into what this is. That's a flexible coupling. I'll tell you why. Well, you might be able to already been able to see why this needs to be there. But essentially, this is just an iron bar. May or may not be laminated. It doesn't really matter. And to this point here, which is about the center, is attached a spring, a leaf spring. Just a flat spring metal that attaches to the frame that hold the magnets and the coils. And that allows this iron to pivot about this point, like that. It does not move this way because of the shape, position, and dimensions of this spring. It does not move this way, and it doesn't move this way. It moves this way in response to energy being put through the coil here. And looking at this, it should be kind of obvious what's happening. Let's say you put a current through this coil that makes it will magnetize this iron here, and it makes this a north pole and makes this a south pole. And should be fairly obvious in what would happen. The north's going to be pushed or pulled toward the south here, pushed away by this north pole, and likely down here, this being south, it wants to go toward the north and push away from the south. So if this were north, would go to this position, like that. Now, these gaps never close, or they never should. They're always open. This moves very, very slightly, not enough to close these gaps. Even if it did, even if you forced this armature over, which you can do, and it contacted north pole to here, if this is no current through the coil, even if you push this over to bottom out on these pole pieces, it still wouldn't. Once you let it go, it would snap back because this spring has enough force applied to keep this centered. But when you've got an alternating current flowing through this coil, this will vibrate. Notice there's an arc up here and an arc down here. That's because that's what this is doing. Because of that, it needs flexible coupling here. This cone can only move that way. You do not want to put forces on it like that. You would just tear the thing apart. If nothing else, it would severely limit the movement of this, which you don't want to do. So there's a flexible coupling in this arrangement between the armature and the cone. I've seen this flexible coupling as nothing but a piece of wire, like a springy, this connecting wire. Very small speaker, but that's what they used. What inspired me to do this is another video I was watching. a guy named Jim Lindinas. I'll probably put a link to the video I'm talking about down below in the description. Or he's servicing a speaker for 1920s, mid to late 20s radio. He's been working on good stuff. And just to clarify what he has is working. That's it. I've seen him before. I've taken him apart, busted him. And what he has works. And my recommendation to him is and was don't mess with what ain't broke. It's functioning. There are issues with this arrangement. These gaps are small, thousandths of an inch. This doesn't move much, but you'll notice I drew this longer down here than it is up here. This distance is shorter than this one. That gives you a bit of an amplification of the arc of the movement. So this needs to be, pretty robust, but this really doesn't move much toward and away from these gaps, but that angle is multiplied by this extra distance down here, so that's why they do it that way. And it's quite effective. It's actually a pretty good plan. Problem is, one of the problems with it is there are particulates in air. Some of them are magnetic and dust, or attached to dust. And if any of that in the air that flows around this, and there will be air flowing around it, anything ferrous or magnetic, nickel and other metals would get attracted right to here and to here and to here and to here. These are these pole pieces where they are closest to this. That's where the most strongest field is. That's where the flux of the magnetic field is the highest, right there. So anything coming through here, drifting by some ferric material goes, attaches itself, and it's without disassembling the whole thing, it's almost impossible to get any of that out because it wants to stick there. It's not just like a dust where you just wipe something in there and it goes away. Anything you try to wipe it away, as soon as you get the wiper away, it jumps off the wiper and goes right back into here. It's not so. Don't disassemble this if you don't have to. I think I've covered it. I think so. Yeah. So, I don't know. Hope this helps. You, Jim, or any of your loyal subscribers. See ya.